The integrated audio infrastructure that served San Francisco's transit corridors, public plazas, and commercial districts operated on a federated network architecture designated SF-PAN, San Francisco Public Audio Network, implemented in phases between 2019 and 2024 as part of the Smart City Infrastructure Modernization Initiative. The system consolidated emergency notification, wayfinding announcements, ambient soundscaping in pedestrian zones, and commercial audio delivery across approximately 4,800 networked speaker nodes using Audio over IP (AOIP) protocol, specifically Dante networking with redundant fiber backbone and Category 6A copper distribution to endpoint devices. Each node, whether a weatherproof column speaker mounted on Market Street light poles, a ceiling array in the Montgomery BART concourse, or a recessed unit in the atrium of the Westfield San Francisco Center, reported to one of 7 regional controllers, which in turn synchronized with a master scheduling server located in the Department of Technology's SOMA data center. The architecture allowed for zone-specific content delivery, dynamic volume adjustment based on ambient noise floor measurements from integrated SPL sensors, and override capability for emergency alerts compliant with FEMA's Integrated Public Alert and Warning System (IPAWS) standards. Normal operation maintained output levels between 65 and 75 decibels A in outdoor environments and 55 to 68 decibels A in enclosed transit spaces, automatically compensated for background noise through a real-time adaptive gain algorithm. On April 19, 2025, at approximately 06:14 Pacific Daylight Time, a scheduled firmware update to the master controller's DSP management module introduced a race condition in the gain staging subroutine that would not manifest immediately but would begin corrupting output parameters across the network as routine scheduling tasks executed throughout the morning. The update package, version 4.7.2 of the Nexus audio management platform, had been staged for deployment during the maintenance window that began at 05 when system load was minimal and most zones were in low activity mode, playing pre-dawn ambient content or silent. The deployment script applied successfully to the master controller without error flags, and automated verification checks confirmed that zone assignments, content libraries, and scheduling databases remained intact. However, the new firmware introduced a modified priority handling system for override events that incorrectly parsed legacy gain ceiling values stored in the configuration database. These values, expressed in the older system as negative decibels relative to full scale, dBFS, were interpreted by the updated code as positive gain targets, effectively inverting the intended attenuation parameters. As morning transit service began at 05:45 and automated announcements for arriving trains triggered across BART and Muni metro stations, the system began applying gain multiplication rather than limitation to output signals. Initial discrepancies were subtle. Wayfinding announcements in the Embarcadero station measured 3 to 4 decibels higher than baseline at 06:22, noticed by station agents but attributed to possible sensor calibration drift. By 06:50, as commuter traffic increased in multiple zones activated simultaneously for rush hour programming, the cumulative effect of incorrect gain staging began to exceed the compensatory range of the adaptive noise floor system. Output levels at street-level nodes along Market Street reached 82 to 85 decibels A at 07:05, with recorded complaints logged through the 311 system beginning at 07:12, describing transit announcements as excessively loud and distorted. The master controller's monitoring dashboard displayed no alerts as the gain values being applied fell within the expanded range that the buggy firmware now considered normal operational parameters. The propagation of audio distortion across the network followed the system's scheduled activation pattern as different zones transitioned from night mode to day mode programming. The financial district's commercial audio zones, which activated at 7:01 to provide ambient soundscaping in pedestrian plazas and retail corridors, began outputting background music at levels between 78 and 83 decibels, rather than the specified 62 to 68 decibels. In the Trans-Bay Transit Center, a multi-zone array serving the main hall experienced clipping in the digital signal chain as pre-amplifier stages saturated, producing harmonic distortion measurable in spectral analysis as significant energy above 4 kHz that was not present in the source material. Automated announcements for bus departures exhibited time domain artifacts consistent with clipping-induced intermodulation distortion, creating a harsh, grainy quality. By 7:30, the system was processing 127 concurrent audio streams across active zones, each subject to the corrupted gain calculations. The digital signal processing chain's look-ahead limiters, designed to prevent output stages from exceeding 95 decibels at 1 meter from any speaker, began engaging continuously but were being fed input signals that had already been amplified beyond design parameters by the master controller's incorrect gain staging. This created a condition where the limiters were compressing heavily distorted signals, effectively brick wall limiting content that was already exhibiting severe clipping artifacts. The result was audio output with a measured total harmonic distortion, THD, exceeding 18% in some zones, compared to the system specification of less than 0.5% THD under normal operation. Frequency response measurements taken later from recorded samples showed significant energy compression in the 1 kHz to 3 kHz range where speech intelligibility normally resides, while also exhibiting boosted low-frequency content below 200 Hz that caused physical vibration in mounting structures. The first systematic documentation of the audio system's behavior came from the Department of Public Health's Environmental Health Division, which received noise complaints beginning at 7:45 from businesses along the Montgomery Street corridor and from residents in the mixed-use towers adjacent to the Embarcadero. Inspectors dispatched with calibrated Type 1 sound level meters recorded sustained levels of 86 to 91 decibels in outdoor pedestrian zones where commercial audio was active, and peak levels of 94 to 98 decibels in transit stations during announcement playback. These measurements substantially exceeded San Francisco's noise ordinance limits, which specify maximum levels of 70 decibels in commercial districts and 55 decibels for sounds audible in residential spaces. The inspector's reports noted that the audio content itself was severely degraded, described in technical terms as exhibiting sustained hard clipping, loss of transient definition, and excessive high-frequency distortion products. In enclosed spaces, such as underground BART stations, the reverberant characteristics of the architecture caused the distorted audio to accumulate in the 500 to 1 kHz band, creating a phenomenon where multiple overlapping announcements, train arrivals, safety messages, and advertising content became unintelligible but remained at high volume. Measurements taken in the Powell Street Station mezzanine at 8:15 recorded a sustained equivalent continuous sound level, LEQ, of 89.3 decibels A over a 5-minute sample period, with peak levels during train announcements reaching 96.7 decibels C. The octave band analysis showed elevated energy in the 1 kHz and 2 kHz bands, consistent with small room resonance modes being excited by the continuous high-level output, and structural vibration measurements detected low-frequency energy at 63 Hz and 125 Hz that was coupling into the station's steel I-beam ceiling. The Department of Technology's Network Operations Center received escalated alerts at 0842 after multiple zone controllers began logging cyclic reconnection events, a symptom of network congestion in the AOIP backbone as the system attempted to redistribute audio streams that were being rejected by endpoint devices detecting out-of-specification input levels. The NOC's initial diagnostic assessment focused on network infrastructure, examining fiber link quality, switch port statistics, and Dante controller synchronization status. All network metrics appeared within normal parameters. Packet loss remained below 0.001%, clock synchronization was stable within 10 microseconds across all devices, and bandwidth utilization on the audio VLAN was at 34% of capacity. This led engineers to examine the audio signal chain itself, beginning with source content verification to rule out corrupted media files. Spectral analysis of the source audio files stored in the content library showed normal characteristics with peak levels between -6 and -3 dBFS and THD below 0.1%, eliminating the possibility of corrupted source material. Attention then shifted to the DSP processing chain where the gain staging error resided, though this was not immediately apparent because the master controller's web interface displayed gain values that appeared reasonable, showing output levels in the 70 to 75 dBA range. However, these displayed values were being read from the configuration database's intended set points rather than from the actual applied values in the DSP engine. Real-time telemetry from the amplifier modules at endpoint speakers told a different story, reporting input signals at levels corresponding to 88 to 94 decibels A, and with measured amplifier clipping occurring in approximately 40% of active channels. The discrepancy between displayed configuration and actual system behavior suggested a software logic error rather than hardware failure or network fault. The decision to implement emergency shutdown procedures was made at 0920 by the Department of Technology's Director of Infrastructure Operations after consultation with the Department of Emergency Management and the transit agencies whose underground stations were experiencing the most severe acoustic conditions. However, the SFPAN architecture had been designed with significant redundancy and automated failover specifically to prevent system-wide outages, meaning that a simple shutdown command could not be executed without physically de-energizing power distribution to speaker nodes. The system's emergency alert capability, mandated by federal standards, required that no remote shutdown mechanism could disable all audio output, as this would eliminate the city's ability to broadcast emergency notifications. The standard procedure for taking zones offline, setting them to a maintenance mode through the master controller interface, was ineffective because the same firmware bug that was causing the gain staging error also affected the mode switching logic. Attempts to place zones into maintenance mode resulted in the system briefly muting output, then automatically re-enabling it and returning to the corrupted high-gain state. The only reliable method to silence specific zones required local intervention at zone controller cabinets to physically disconnect power or disable amplifier modules. The city's electrical crews were dispatched to 23 locations housing regional and zone controllers, but accessing these required coordination with building management and in some cases cutting locks on equipment enclosures that were not regularly serviced. The process of physically disconnecting zones began at 0955 in the financial district and expanded outward, but the geographical distribution of controllers meant that large areas of the city would continue experiencing high-volume distorted audio for several hours. Meanwhile, zones that had not yet been de-energized continued operating in the degraded state, with audio quality deteriorating further as thermal stress on amplifier modules, now operating continuously at near maximum output, began causing additional hardware-level failures, including blown voice coils and speaker drivers, and protection circuit shutdowns that briefly silenced individual speakers before the system's automatic diagnostics attempted to re-enable them. The acoustic environment in areas that remained active under the failed system state exhibited characteristics that were documented through both instrumented measurement and architectural analysis. In the Yerba Buena Gardens, where a distributed speaker array provided ambient soundscaping across the 5.5-acre site, sustained output at levels between 84 and 89 decibels A created a pressure field that reflected off the surrounding high-rise facades, producing a reverberant condition with measured decay times, RT60, in the 2.3 to 2.8 second range for frequencies between 500 Hz and 2 kHz, substantially longer than the open-air acoustic environment would normally exhibit. This reverberation caused successive audio events, programmed nature sounds, announcements, and commercial content to overlap temporally, creating a dense, unintelligible acoustic texture. In underground retail spaces, such as the BART concourse level beneath Market Street, the combination of hard parallel surfaces and continuous high-level output produced standing wave patterns at frequencies corresponding to the dimensional resonances of the space. Measurements documented modal peaks at 73 Hz, 146 Hz, and 219 Hz, with amplitudes 12 to 15 decibels above the broadband level, indicating that specific frequency components were being reinforced by the room geometry. These low-frequency components, while not directly part of the speech content being broadcast, created a sensation of physical pressure and induced vibration in lightweight construction elements, including suspended ceiling tiles, glass storefronts, and ventilation grills. At the Westfield San Francisco Center, a 4-story atrium with a glass roof structure, the combination of upward-firing ceiling speakers and highly reflective surfaces produced an LEQ of 91.2 decibels A, measured at the ground floor at 10:30, with speech intelligibility metrics, STI, degraded to 0.31, categorized as bad on the standard scale, where 0.5 represents the minimum for acceptable speech communication. The continuous exposure to these sound pressure levels over extended periods represented conditions that would require hearing protection under OSHA workplace noise exposure regulations had they occurred in an occupational setting. The zone-by-zone shutdown process continued through mid-afternoon, with the final deactivation occurring at 14:47 when power was disconnected to the Embarcadero Station's public address array. The geographic pattern of silenced zones created a patchwork acoustic environment across the city, where some areas returned to normal ambient conditions, traffic noise, construction activity, human conversation, measuring typical urban levels of 55 to 68 decibels A, while adjacent areas, still under system control, maintained the distorted high-volume output. This created spatial discontinuities where pedestrians moving between blocks experienced abrupt transitions from degraded system audio to urban quiet, with measured level changes of 25 to 30 decibels A occurring over distances of less than 50 meters. In some cases, audio from still active zones coupled into deactivated areas through acoustic propagation paths, doorways, ventilation openings, and canyon-like street geometries, producing a secondary exposure at reduced but still elevated levels. The transit agencies implemented modified service during the shutdown, operating trains without station audio announcements and relying instead on onboard public address systems and visual information displays. This operational mode was feasible for BART and Muni Metro because vehicles maintained independent audio systems, but created accessibility issues for passengers who depended on audio announcements for navigation. The commercial zones presented different challenges as the audio infrastructure there served multiple functions, including background music for retail environments that was often specified in lease agreements. Building management systems in several locations attempted to bypass the disabled SF-PAN infrastructure by activating older backup audio systems, only to discover that in many cases these had been decommissioned when the integrated network was installed. By 1500, approximately 94% of the SF-PAN had been powered down, with only a small number of zones in the Mission District and the western neighborhoods still active due to crew access delays at controller locations housed in secured municipal facilities. Post-event analysis of the system logs and recorded audio samples began immediately under the direction of the Department of Technology's Enterprise Architecture Division, working in coordination with the audio system integrator and DSP platform vendor. The firmware update package, version 4.7.2, was identified as the root cause after comparative analysis of the DSP engine's gain calculation routines between the previous stable version, 4.6.8, and the failed version. The specific error resided in a function named calculate output gain within the override priority handler, where a variable type conversion from the database's floating point DB values to the DSP's fixed point register format incorrectly applied a sign inversion. The code review revealed that this function had been refactored in version 4.7.2 to improve performance by reducing the number of conditional branches, but the optimization introduced the type conversion error that was not detected during the vendor's quality assurance testing because their test database used only positive DB values for verification. San Francisco's database contained legacy configuration entries with negative dB values dating to the system's initial deployment when a different gain referencing convention was used. The cumulative effect of this error across 4,800 speaker nodes resulted in approximately 31 terabytes of distorted audio being broadcast over an 8-hour and 33-minute period, measurable through the system's network traffic logs, which recorded all AOIP stream data. Spectral analysis of recorded samples from 17 different zones showed consistent characteristics: average THD of 14.2%, intermodulation distortion products at -20 to -18 dBc, and clipping-induced artifacts present in 98.7% of analyzed frames. The amplitude distribution histograms of the recorded material showed asymmetric clipping with 63% of samples at or near maximum positive digital values, confirming sustained hard saturation in the digital domain before the signal reached the analog output stages. The formal incident report compiled by the Department of Technology documented the timeline, technical root cause, immediate response actions, and system performance data across 47 pages, with 23 supporting appendices containing log excerpts, acoustic measurements, and network telemetry graphs. The report noted that the event constituted multiple violations of San Francisco Noise Ordinance Section 2909, specifically regarding the maximum permissible noise levels in commercial and residential zones, and also represented non-compliance with the system's design specification for emergency notification audio quality, which required intelligibility metrics meeting or exceeding NFPA 72 standards for voice clarity. The vendor-provided post-incident analysis included revised quality assurance procedures requiring validation against databases containing both positive and negative legacy values, implementation of hard-coded maximum gain limits in firmware that could not be exceeded regardless of database configuration, and addition of real-time audio quality monitoring that would detect THD above 2% and automatically trigger system degradation alerts. The revised firmware version 4.7.3, incorporating these changes and reverting the gain calculation logic to the previous stable implementation, was staged for deployment but not immediately applied, pending extended validation testing against a full replica of San Francisco's SF-PAN configuration. The incident was classified as a Category 2 service disruption under the city's IT governance framework, requiring external audit of the change management process and mandatory review of all safety-critical audio system configurations across city departments. The Department of Emergency Management initiated a review of public alert redundancy, examining the dependency on the SF-PAN for IPAWS message distribution, and evaluating whether cellular-based alerting and traditional outdoor warning sirens provided adequate backup notification capability in scenarios where the integrated audio network was unavailable or degraded. No timeline was established for full system restoration to normal automated operation.